Assalamualaikum warahmatullahi wabarakatuh dan salam sejahtera. Selamat bertemu kembali di Syahnun Channel, saluran pendidikan anda. Kali ini kita akan meneruskan Introduction to Organic Chemistry, subtopik Isomerism, Part 2. Jadi tanpa melengahkan masa, mari kita mulai. Okay, Chapter 11, Introduction to Organic Chemistry, Isomerism, Part 2. Our objective today to define stereoisomerism. Okay, today is stereoisomerism. Describe cis-trans isomerism due to restricted rotation about carbon-carbon double bond and single bond in cyclic compound. And then identify cis-trans isomerism of a given structural formula. Define chirality center and enantiomers. Identify chirality center in a molecule and explain optical activity of a compound. And the last one, of course, draw a pair of enantiomers using 3D formula. Okay, we go to the definition of stereoisomers. Isomers that have the same constituent means order in which their atoms are connected, but differ in the arrangement of their atoms in space. Okay, space ni bukan angkasa lah, ruang. Okay, arrangement the atom di dalam ruang 3 dimensi. Enantiomers. Okay, what is enantiomers? Stereoisomers that non-superimposable mirror images of one another. That means that kita sambung daripada definition ini, blah 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 blah, and then that non-superimposable. Okay, so we make it shorter, so we just use stereoisomers. Okay, stereoisomers ni dia lah, panjang ni. Diastromers. What is diastromers? Stereoisomers whose molecule are not mirror images of each other. Okay, dia berlawanan lah dengan enantiomers. And cis-trans isomers. Stereoisomers due to restricted rotation about carbon-carbon double bond in alkene and single bond in cyclic compound. Okay, ini cyclic alkyl lah ni. And stereoisomers ini sebenarnya merujuk kepada diastromers. Cis-trans isomers dia di bawah stereoisomers. Okay, not mirror images of each other and due to restricted rotation about carbon-carbon double bond in alkene or single bond in cyclic compound. Okay, we go to the cis-trans first. Cis-trans or geometric, ni buku-buku yang lama dia guna geometric isomers. Okay, cis-trans isomers have same molecular formula and same order of attachment of atom, but differ in how the atom or group of atom are oriented in space. Okay, and occur in compound in which free rotation is prevented by the presence of carbon-carbon double bond or in a cyclic structure. Okay, and then we have a requirement for cis-trans isomers. Number 1, restricted rotation about carbon-carbon double bond in alkene or single bond in cyclic compound. Okay, this is first requirement for cis-trans isomers. And number 2, each carbon atom of a site of restricted rotation has 2 different groups attached to it. Okay, this is the second requirement. And cis isomers. Okay, what is cis? We have a cis-trans isomers now. We want to know which one is cis, which one is trans. Okay, when the molecule has these 2 requirements, and then we want to characterize it as a cis or trans isomers. For cis isomer has 2 same group or atom on the same side of the double bond. Okay, this is for cis isomer. For trans isomer has 2 same atom group of atoms on the opposite side of the double bond. This one is same side. This one is for trans opposite sides. Now we go to the example. For example, is 2-butene. Okay, if we write this molecular structure of 2-butene like this, CH3, CH, double bond CH, and CH3. This one we cannot see the cis-trans isomers. To make it cis-trans isomers, we have to draw in three-dimensional. All right, this is a three-dimensional structure of 2-butene. Okay, see this one. Okay, let me take my pen. Okay. How to draw it? Okay. Okay. Okay, first we look at this carbon-carbon double bond, CH double bond CH. So we draw like this carbon-carbon double bond and make it like this. Why? Because for carbon-carbon double bond, we know that this is sp2 hybridized carbon. sp2 hybridized carbon, the shape of sp2 hybridized carbon is trigonal planar. Okay, this is trigonal planar with the angle of 120, 120, and 120. That's why actually we are draw this structure in three-dimensional. Okay, because this is sp2 hybridized with trigonal planar shape. Okay, we draw like this, and if you look at here, for this carbon, it has hydrogen and CH3. So we just draw hydrogen here and CH3 here. And look at this. Okay, look at this. Look at this. It also has H and CH3. So we can draw H here and CH3 here. Okay, so it's become like this. And we have another option. The option is I want to change H up here and CH3 here. So it will become like this. H on the top and CH3 on the bottom. Okay, and for this side, we just maintain H up there, up here, and CH3 down here. Okay, for this 2-butene, actually we can draw two different type of molecule. Okay, two different type of molecule. We call it cis-trans isomers. Okay, and then for the okay, look at here. The hydrogen here situated at opposite side, so we call it trans. And for hydrogen here at same side, so we call it cis. This is how we name it as a trans and cis isomer. Okay. First, we have to know the molecule should has two requirement. The requirement is a restricted rotation. In this case, the restricted rotation is carbon-carbon double bond. The second requirement is two different atom or group of atom attached to carbon-carbon double bond. Now we have H and CH3, different atom or group atom. Also here, CH3 and H, different. Okay, the two requirement, uh, are there, and then we just change the position, and then we can write the name of it, whether it is trans or cis. Okay, let me make it clear again. So this is cis and trans 2-butene. Okay, the second example, we have a cyclic compound. Okay, this is 1,3-dimethyl cyclohexane. As we can see that the atom here is hydrogen and CH3, hydrogen and CH3, two different group of atom, and then the H here, the H at the same side, so this is cis. And for the second structure, the H here at opposite side, so this is trans. Trans 1,3-dimethyl cyclohexane. Alright. Okay, this is the model of cis-trans isomers. Okay, look at here. This is double bond here, double bond, and here is the black one, the black ball, and the green one. Okay, different. So different group of atom, different group of atom also. Okay, this one also different group of atom, different group of atom. Is, as we can see, this is actually trans. Okay, this is hydrogen. Okay, same hydrogen. This is cis. When we try to superimpose mean, okay, we try to superimpose this one, and then we can see that it cannot. We cannot superimpose these two molecules because this is different different compound, okay, but they are isomers because attachment of atom, this carbon attached to the black one, um, and then green, okay, this one also black and green, and here we have green and also brown here, brown, okay, same attachment but cannot superimpose, and it has a double bond restricted rotation, so this is cis-trans isomers. Okay, if one of the doubly bonded carbon has two identical groups, cis-trans isomerism is not possible. For example, this one. Okay, this carbon has carbon-carbon double bond, but CH3 and CH3, two groups of atom attached to the carbon-carbon double bond. Okay, this is the second requirement is not applied here. So this is not cis-trans isomers. Okay. The cis-trans isomers have similar chemical properties but different physical properties because different spatial arrangement of the group and polarity of the molecule. Okay, the cis-trans actually it has different polarity. And for example here, stability. Trans isomer more stable than cis isomers. Okay, and for the melting point, cis isomers, the melting point of cis isomers is less than trans isomers, and for the boiling point, the cis isomers are greater than trans isomers. This is actually because of polarity, yeah? Because the cis isomers is more polar than trans isomers. Okay, you will learn it in tutorial class. Yeah, why cis isomers more polar than trans, and why cis isomers the melting point of cis isomers less than trans isomers. Okay. Okay, here we have a exercise. Which of these shows cis-trans isomerism? Okay, look at here. Look at here. This actually this is no cis-trans isomers because of this. We have two CH3 attached to the carbon-carbon double bond. So this is this structure do not show cis-trans isomers. And what happened to here? Yes, here we have a cis-trans. If it has a cis-trans, we have to write the structure. Okay, I write the structure of this one. First, we look at the carbon-carbon double bond. C, and then make it like this. If, okay, I will make it bold, this color, okay. Okay, like this, you have to make it like this. If you draw like this, okay, for example, This is wrong because this is the shape of trigonal plana. This is not the shape of trigonal plana. And so like this is all are wrong. Okay, this is not trigonal plana of carbon-carbon double bond. The carbon-carbon double bond must be like this, trigonal plana 120 degree. Okay, and then we have a H here and C6H5. So I'll make it H here, and C6H5 actually is benzene ring like this, and I have a H here and Br. Okay, this is cis isomers. Okay, this is cis isomers because H and H. And then I want to draw the trans isomers. Okay, like this. First, make it this one as okay. I just want to change the H and Br here. This is Br, this is H. So this is cis isomers and this is trans isomers. Okay. Okay, number three. Okay, number three, we don't have a cis-trans isomerism because we have two identical substituent here, and here also we have two identical H, 2H, and 2H, and so on. So no cis-trans isomers. For this one, yes, here we have cis-trans isomers. Okay, I want to draw it. Okay, now I want to change the OH, let me see. Okay, make it like this. Okay, why I change? Because when we want to draw this structure for a cyclic, make sure that, okay, like this. Make sure that we have a up and down like this. If we copy this structure, when we try to make it up and down, so like this, this one will interfere the bond of carbon-carbon here. Huh? We cannot see the covalent bond here. But this one we can see the covalent bond here, covalent bond here. Okay. Alright, okay, I just write it here. Okay, I have a OH here, OH here, because this is cis and H and H. This is cis trans, and the trans, the trans like this. Okay, OH and H, and here is OH and H. This is trans. Okay, this is cis. All right. And the last one, okay, we have a Cl and H. We have H and Br. Also, this is cis-trans. Okay, you can write it on your own. Okay, now we go to the chiral. What is chiral? The lady is holding one hand in front of the mirror and one hand behind. Okay, as we can see, the mirror, this is a mirror image of her hand. Left hand and right hand are mirror images of each other. Okay, this is our hand, and then this left and right hand cannot superimpose each other. Superimpose means, okay, I try to superimpose like this. This is my thumb. This is my thumb. Cannot superimpose. Cannot like this. Okay, cannot superimpose. Non-superimposable. So we call it right hand and right hand and left hand. Chiral. We call it chiral. Chirality arises from a lack of symmetry. Okay, lack of symmetry is called asymmetry. Okay, we can use asymmetry or lack of symmetry or unsymmetry. Okay, And for chirality compound, actually it has what we call optical optically active. Okay, what is optically active compound? We'll see. Optically active compound are chiral compounds. So now we want to see optical activity now. Okay, what is optical activity? Some of the stereoisomers are optically active. The compound differ in the effect of plane polarized light. Okay, now we have a term plane polarized light. What is plane polarized light? The light, after passes through a polarizing filter, vibrate in one direction. The light is called plane polarized light. This is what is plane polarized light. And then these stereoisomers rotate the polarized light, and the angle is measured using a polarimeter. And optically active compound exists in two isomeric form. Isomers rotate clockwise is dextro-rotatory isomers. We use plus isomers, and isomer rotate anti-clockwise levo-rotatory isomers. Okay, look at here. This is light source. This is our ordinary lamp, for example. Our ordinary lamp is unpolarized light. Unpolarized light means um, the light now vibrate at any direction, okay? Many direction. This is our source of light. For example, our sunlight, our ordinary lamp, and so on. All are unpolarized light. Okay, the light vibrate, okay, at many direction. When it pass through polarizer prism, then the polarizer will screen the light, and only one direction or one vibration of light. Okay, like this, only one direction of light can pass through this polarizer prism. Okay, this we call it polarized light. Okay, before polarizer prism, we have many direction of vibration of light. Now only one vibration, like this. And then here we have a our sample here. When this light pass through this sample, we can see that this sample will rotate the polarized light. In this example, it will rotate clockwise, okay, with some degree of rotation. Okay, some degree of rotation. Here we have a angle scale, and this is our eyes, so we can measure the angle of rotation. Okay, and this we call it a polarimeter. Polarimeter. Uh, our sample is here. Okay, and for sample that can rotate plane polarized light, we call it, this sample is optically active. Okay, if we have a sample that cannot rotate plane polarized light, so that sample is not optically active. Okay, and for optically active compound, of course, it has a requirement for that. Okay, we look at the requirement for optical active compound. Okay, number one, molecule contain a chirality center or stereogenic center or asymmetric carbon. So this is the first requirement for optically active compound. Okay, not all compound can rotate plane polarized light. This is the requirement number one. What is chirality center? The chirality center is sp3 hybridized carbon atom, this one, with four different group attached to it. Okay, this is sp3 hybridized carbon. That means the carbon must has only single bond. Okay, cannot double bond. Double bond sp2. Okay, this is sp3 hybridized carbon, and with four different groups attached to it. And number two, molecule is not superimposable with its mirror image. Okay, if we draw the mirror image of the compound and the mirror image is not superimposable, so this is two requirement for the optically active compound. Okay, like and for optical active compound, we have to draw the 3D molecule like this. Okay, we call it dash, wedge, line, wedge, and dash projection. Okay, we call it. This one is dash. No, we call it line, dash, and wedge projection. Okay, we have two line here. Okay, two line here, and here we have a dot 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 here. Dot dot here is uh, uh, dash, and we have a wedge here like this, the bold one here. Okay, what does this mean? This means this is in a plane. This project out for the wedge here, and this one is uh, out of plane. Out of plane. This is plane. Okay, the line is plane. This is ke depan kita. Okay, and this is ke belakang. Okay, now we try to draw the mirror image of this molecule. Okay, like this. And here, the S here, near to the mirror. And here also we have a mirror, the S near to the mirror. And Q, okay, this is Q here. And P here. And this is R. Okay, this is mirror image of this compound. Okay, look at this, the model here. A pair of stereoisomers with a structure that a mirror image. Okay, but not superimposable. Okay, look at this. We have a sp3 hybridized carbon here. This is carbon with four different. Okay, the color is different. Okay, the green, yellow, blue, and red. Okay, this is mirror image. Imagine that here we have a. Okay, imagine here we have a mirror. We have a mirror here. Okay, this is our mirror. Okay, okay, this is the macam kepala lah. Okay, this is the red one, the blue, and the green. Okay, when we try to superimpose, okay, look at here, not superimpose, not superimpose. That means this is not identical molecule. This is different identical. We call it enantiomers. Why we call it enantiomers? Because it has chirality center here, four different group of item, and the mirror image not superimposable. So this is enantiomers, different compound, and the different compound is actually is enantiomers. Okay, all right. This pointer. Okay, wait, pointer. Okay, wait, pointer option, highlight, erase. I want to go to the arrow. Okay, now we look at the this one is identical molecule. Okay, imagine that we have a mirror here. Okay, still mirror. Oops, mirror here. Sorry. Mm, okay, okay. Imagine that we have a mirror here, and this is not mirror images because this is the blue one. This is a green, so this is not mirror image. when we try to superimpose, yes, this can be superimposed. Look here, look at here, the green, the yellow, and the blue, and the green, the red one. Okay, they can, both of them can superimpose. So this is not mirror images of each other and superimposable. So this is identical molecule. Okay, so now we go to the enantiomers. Enantiomers are a pair of stereoisomers with structures that are mirror images of each other but non-superimposable. For example, we have a molecule like this. Okay, four different. This one is CH3, this one is H, OH, and CH2, CH3. Four different item of group atom of each attached to this carbon. So this is first requirement, and the second requirement is mirror image. We call it two butanol, and here we have a plus here. Plus means it will rotate plane polarized light clockwise. Okay, dextrorotatory. This is dextrorotatory. It will rotate plane polarized light rotate plane polarized light clockwise. Okay, and then now uh, okay, we draw the mirror image of this compound two butanol. So this is two butanol also, but this is negative sign. Negative sign here means this compound will rotate plane polarized dextrorotatory anti-clockwise. Okay, with the same magnitude. Okay, the pair has identical chemical and physical properties. Okay, the pair differ in the direction of rotation of plane polarized light, but the magnitude of direction is the same. Okay, differ in rotation, direction of rotation of plane polarized light. Okay, now we have a exercise here. This compound optically active compound. Okay, look at this. Okay, as usual, I will change it to the bowl. Okay, now it's bowl already. Okay, first we try to find the um, chirality center. Okay, this carbon no chirality center because this carbon attached to 3H. Yes, this carbon as a chirality center. Okay, this carbon no. Okay, how to draw it? Okay, I look at here, this carbon. I just draw like this, C, and then like this, and then okay, make it bold, and so on. Okay, okay. Now, to make it easy for us to look, I will draw this one, COH, on top of this. So easy for me to draw the second isomers, okay, the enantiomers. And the rest is I have a H here, okay, I will put H here, and CH3 here, and NH2 here. Okay, oops, okay. Now I just draw the mirror image of this compound like this. Okay, look at here. This one is H. This one is COH. Then okay, the bold one here. We call it wedge. And this one is dash. The dash is CH3. And the bold here is NH2. Okay, this is a pair of enantiomers. Okay, a pair of enantiomers. Because I draw in three-dimensional, which line, which dash projection, we call it, and then I draw the mirror image of this, and then I get a pair of mirror image. Okay, look at here. Okay, oh no, B B is not um, optically active. Why? Why? Because look at C here. This C here attached to 2CH3. Okay, 2CH3. So this is not Chirality center. Okay, look at here. Okay, this carbon. This carbon attached to this one H and 2Cl2. So also this is not a optically active compound because no chirality carbon. Okay, look at this. This is this carbon no. This carbon also no because 2H. This carbon yes. This carbon has four different group of atom attached to it. H, CH2, CH3, Cl and CH2Cl. Okay, I just use this one. Okay, now I want to draw it. First, I will use this one. CH2, CH3. Okay, CH2, CH3. This is the tips how to draw the enantiomers. The bulky one, we draw on top or on bottom here. Okay, and then the small one, like here we have hydrogen and chlorine. Okay, hydrogen here and chlorine here. So easy for us to draw its enantiomers. And we have a CH2Cl here, CH2Cl. Okay, and then oops. Okay, easy for us. This one is Cl. This one is H. This one is CH2, CH3. This one is H2Cl. Okay, look at here. Yes, this one, C, because we have hydrogen. Oops, H, hydrogen. No, because this is hydrogen. Also here is also hydrogen. One. Oh yes. One, two, three. Oh, okay, yeah. This is one. This is H. Yeah, this is also. Um, it has chirality center. Let me draw the structure. Yes. Okay, make it clear. Number one is this one. CH. CH. CH3. 2. Okay. 1, 2, 3, 4. And and then H. Okay, I want to put here H. And then OH. And then CH3. Okay, four different group of atom. OH, CH3, and CH3 2. Alright, so you can draw the enantiomers of this compound. And here is no, this is also, and for this one also yes. We have a benzene here, we have a H, we have a CH3 and CN. 1, 2, 3, 4. This is also a chirality center. It has a chirality center. So this is optically active compound. Okay, let's see. I want to put benzene here, and I have CH3 here, CN here, and H here. Okay. Okay, this is the differences between lemons and oranges. As we can see that the difference in here, the chirality center here is here. This one, I just draw the asterisk, asterisk. Okay, two line here, and now this is wedge. This is dash. The wedge is a mirror image each other, and also the oops, the the line, the dotted line here, mirror image each other. So it's become lemon and becomes oranges. Okay, the last one. This is the last exercise for this chapter. Indicate with asterisk, asterisk this one, the chirality center, and drop a pair of enantiomer for each of the following compound. Okay, yes, I have one chirality center here. And here, yes, we have one chirality center here. And here, looks like all have a chirality center. Here, no, no, but this one, yes, this one also. Okay, all has a chirality center. I just want to draw one of them. Okay, let me choose this one. Let me choose this one. This is I just put the asterisk here, ch, and then okay, C line. We can change the line to be here, no problem. And then this is okay. Okay, now I want to put this one. This one is bulky group, so I want to put on top here CH3 2. And then the second bulky, I think this one. Okay, CH2, CH3. And the rest is H and OH. Okay. And then we just draw the mirror here, mirror on the wall. Okay. Oops. Okay. Okay. On top here, CH3 2, OH here, H here, and CH2, CH3. Okay. This is for today. Okay, untuk isomerism part 2 kita dah cover, dan jumpa lagi di bab yang berikutnya, iaitu reaction in organic compound. Sekian, Assalamualaikum warahmatullahi wabarakatuh, dan salam sejahtera.